I'm going to go ahead and turn it over to our presenter today, President and CEO of Connexus, Ed Marzell.
All right, thanks, Chris. I gave this presentation at the Global Congress on Process Safety earlier this year. This is a little bit about me. Most of you know me. There's a lot of information about me on the internet, on our website. I'm the president of Connexus. I've been doing this technical safety thing pretty much my entire career. I'm on the ISA 84 committee, the IEC 61511 committee, wrote a whole bunch of books, blah, blah, blah. And with respect to this topic, I am actually also a co-developer of Connexus's Arbor fault tree analysis software, helping to write the associated manuals and training. So things like the minimal cut set analysis algorithms, I know that very well because I helped to write the code. All right. So the presentation that I gave at GCPS was called Use Fault Tree Analysis When Lopa Fails. And at the Global Congress on Process Safety, you've got 20 minutes to give a presentation and 5 minutes for Q&A. And which is why I like to do these reprises of this topic, because I have more time. 20 minutes is just not enough for a topic this complex, let alone to get into detail with answering the question. So I'm happy for this venue so I could go in a lot more depth and cover it in the level of detail that I think is appropriate. So what's our starting point? Lopa, Layer of Protection Analysis. It's a tool that lots of people use for a lot of different applications. It's ubiquitous. And it's ubiquitous, it's used a lot, but at the same time, you have to understand that it's very simple. It's a simple tool. It was developed by several engineers, myself included. I like to say that when I invented Lopa, I called it simplified fault tree analysis, but the guys at Roman Haas had a catchier name. So you call it Lopa because that's what they called it, but you're generally using my math, which is the simplified fault tree math. But I digress. I don't want to go down too far down that road. So Lopa was developed to be kind of the middle ground in between the purely qualitative HAZOP and the fully detailed quantitative risk analysis, giving you a little bit more detail, but not requiring massive quantities of time to complete. So in the chemical process industries, there are a lot of policies and procedures that are employed by companies to take the starting point of a HAZOP scenario and bring it into Lopa when more detail is required. So when is more detail required? Well, number one, if the HAZOP team thinks more detail is required, that's generally a good indicator that more detail is required. But beyond that, a lot of times Lopa gets performed when the consequences are high. So if the HAZOP team says there's a fatality or a potential fatality as a result of this event, they might want to not just use the qualitative HAZOP and switch over to the semi-quantitative Lopa. Also, the thing that got me into Lopa was, I come from the instrumentation and control side of the fence, and I'm designing safety instrumented systems. And when I design safety instrumented systems, I need that safety integrity level, or the numerical target that defines the quality of the safety instrumented function that I'm defining. So if I have a scenario that uses a safeguard that requires a quantitative performance target, I'm going to need to go into Lopa to develop that quantitative performance target. So those are the things that trigger Lopa. And remember, when Lopa was developed, its intention, now this is more than 20 years ago now, the intention was that it is an order of magnitude technique. So it's going to be more detail than a HAZOP, but less detail than a QRA. The other thing that was key to layer protection analysis is that it was really focused on preventive independent safeguards. Preventive meaning if they work, there is no consequence, as opposed to things that just make the consequence smaller. And independent meaning physically and functionally separate from the initiating events and also the other independent protection layers. But As we have applied Lopa over the past couple decades, we have found that it is ineffective in some cases. And when I gave this presentation at GCPS, I had someone request that I put together a list of all the situations where Lopa will not work. And I'm thinking about doing that, making that a paper for next year, but we will see. Yes.
Excuse me, Ed, there's a question here. Did you submit a paper for this at the conference?
Yes, I did. I submitted a paper at the conference. The paper is published in the proceedings. If anybody wants a copy of the paper, send an email to myself or to Chris or info@connexus.com and we will send it to you. Okay, so Lopa uses a lot of simplifications, and sometimes those simplifications have a marginal effect on the result and make Lopa useful. Sometimes the simplifications completely blow up and make the Lopa ineffective right out of the gate. So some common situations where Lopa is going to fail. So if the initiating event is loss of containment, this pipe leaks. Well, preventive safeguards aren't going to help you when the initiating event is loss of containment. So in that case, your risk reduction needs to reduce the frequency of the loss of containment, which is kind of outside of the Lopa world. When you use consequence mitigation, such as fire detection, turns on an automatic spray system to put the fire out. Well, in that case, you still have a fire. There's still a consequence you need to deal with. So that's a little bit tricky. That was actually the subject of my GCPS paper from 2 years ago. If anyone's interested in that, I'd be happy to send that to you also. Intermittent and batch operations don't really, they don't make Lopa ineffective. They just make it clunky to do because your initiating event is not some sort of dangerous failure. It's like, how many times do I do a batch a year? Which it's clumsy as opposed to wrong in those situations. Now, the ones that I have highlighted in yellow are the ones that we're going to be focusing on today, which is protection layers employ common shared subsystems. So if I have multiple protection layers all going through the basic process control system, I am sharing at a minimum the CPU, the basic process control system. They are not independent. How do I handle that? Lopa, pure Lopa can't handle that, so you have to make some assumptions. Also, cases where there's extensive human interaction can sometimes make Lopa, shall we say, a little bit awkward. Now, the oversimplifications that we do in a Lopa sometimes are going to lead to suboptimal design. Let me give you a perfect example. And one of the people that I believe is in attendance from a refiner once asked me the question, you're looking at 9 transmitters here, but he noted that usually they have 5. And I'm like, yeah, that's a problem, but you can't really deal with that problem until you leave Lopa and do something different. Okay, so here's an example. We have a fired heater. And as most of you know, on a fired heater, if the fuel gas pressure is too high or if the fuel gas pressure is too low, that could result in a flame out, which through a series of unfortunate events could result in a firebox explosion, potentially even with a fatality. So let's propose a design that could potentially be generated by a layer of protection analysis, which requires complete physical and functional separation. You would say, well, I've got one transmitter. Let me pull out my magic pencil and write on the screen. I've got one transmitter for my control loop, and I need that to be separate from the transmitter I need to take credit for my low pressure alarm. Well, I also need a high pressure alarm. And for my low fuel gas pressure, I need SIL2. So I'm going to do a 2 out of 3 vote for my shutdown system. And well, I've got high fuel gas pressure. Obviously, high fuel gas pressure and low fuel gas pressure are different. So I've got a 2 out of 3 vote for that. totaling 9 transmitters on the fuel gas. Seriously, I need to measure the fuel gas pressure 9 times. 8's not enough. 7's not enough. I need 9 transmitters. This is crazy. This is comical. Now, granted, the high fuel gas pressure scenario and the low fuel gas pressure scenario are separate from each other. So you don't need to have independence between those. But even if you did that, you'd still have 5 transmitters. 5. Is that really necessary? 4's not enough. Think about this. When you're doing your SIL calculations and you consider common cause failures, a common cause failure of 5% or even as low as 2% will tell you that adding a second transmitter in addition to the first transmitter is a substantial benefit. Adding a third transmitter in addition to the second transmitter is marginal to negligible benefit. The fourth transmitter gives you absolutely no benefit whatsoever. It disappears in the insignificant digits of the common cause failure probability. So what are we doing? Well, we're putting all of these extra pieces of equipment in because we need each piece of our Lopa to be separate. Because the bottom line is Lopa's math can't handle a shared component, but fault tree analysis can. That's why sometimes you might want to switch over to fault tree analysis to look at some of these scenarios. So looking at fault tree analysis, and I've got an example fault tree of a small subsystem I'll get to in a second here. Okay, so in fault tree analysis, we're going to calculate the frequency of the probability of a top event up here based on basic events. So the individual equipment items failures, and then we're going to process that through a series of gates that will tell me logically how are the failures of those individual components related to each other. It's going to allow for a more detailed assessment than Lopa can do, because you're capable of doing more complex logic. We can do AND gates, we can do OR gates, we can even do voting gates. Also, the key for our case study here is that the fault tree analysis is going to allow for elegant handling of shared components because we solve things using something called minimal cut set analysis. More on that coming up. So that's what we're going to do with our fault trees. Now look at this fault tree on this page here. What we're calculating is the probability of failure of actually, I'm not going to talk about it on this slide. I'm going to talk about it on the next slide, where we're going to talk about a valve subsystem. Okay, actually, it's a few slides from now. I got a little bit more. Fault tree analysis will also allow you to do sequencing, and it does a lot of this sequencing for you automatically. Now, what you may or may not appreciate about Lopa is that it has built-in sequencing. The initiating event is an initiator, and then the protection layers, or more correctly, the failure of the protection layers, are enablers. So I have an event that occurs, and I have other events that enable that initial failure to propagate to a consequence. In fault tree analysis, you can define events to be initiators, you can define events to be enablers, or if you make no definition, like you see on this last event here, the software will assume that it's both an initiator and an enabler. Hey, what the heck does that mean? Let's say I have a dual pump system, and in order for my event to occur, both of those pumps have to fail. In that case, both of those pumps are both initiators and enablers, depending on which one fails first. So in that sequence, the first pump to fail is in the failed state, and then a second pump fails. The second pump failing is the initiator. The first pump being in the failed state is the enabler. So fault tree analysis sophisticated software tools like Connexus's Arbor will do all of that math behind the scenes for you if you didn't define it. But you need to be smart enough to define it, especially if you're replacing your layer protection analysis with a fault tree. Defining what are initiators and what are enablers is going to be critical. Okay, so if you look at a typical layer protection analysis as a fault tree, it's going to look like this. And this is with one initiating event. I have an initiating event. It is an initiator, and it has a frequency associated with it, which you see the little W there means it's going to be a frequency. And I have my time units set up in terms of years. Now, the top event, the consequence that we're trying to prevent will occur if the initiating event occurs and all of the protection layers fail. So this flat bottom here tells me I have an AND gate. So I have an initiator and all my protection layers fail. Now the protection layers fail. We have another AND gate here, flat bottom, that says basically all the protection layers. And in this example, I have 3 protection layers. So all the protection layers fail if protection layer 1 fails, and 2 fails, and 3 fails. The protection layers are defined as enablers and given probabilities. So the Q is an unavailability in fault tree analysis language, but it is a probability that the device will not work. Okay, so that's your standard fault tree. And in this, Lopa is a fault tree. And in this paradigm, the initiating event, the protection layers are all 100% physically and functionally independent of each other. Now, the next thing that we would do is we would solve the fault tree. And this is where the magic of fault trees is going to become evident to you. I've created an example of a shutoff valve system. And I said, I need for 2 shutoff valves to close to get to a safe state. That's why you see the little kind of the curved bottom here makes this an OR gate. So everything with a curved bottom is going to be an OR gate, meaning if either one of the things underneath it is true, the result is true. Now, so I need both of these valves to close to get to a safe state. But for each valve, it will fail to get to the safe state if either it's stuck in position or the power supply for that valve fails. Okay, and there's a probability of 0.1 that it'll get stuck and a probability of 0.1 that I have a power supply failure. So now, how do you solve for the top gate? Now, if you're new to fault tree analysis and you're thinking logically, you're thinking, I'm going to solve gate by gate and work my way up. So an OR gate is a logical OR, which is probability addition. So 0.1 plus 0.1, 0.1 should give me 0.2, but instead it gives me 1.9. Why is that? Well, you force me to draw Venn diagrams. So I have the probability that event A happens. I have the probability that event B happens, but there's also this probability that A and B will happen simultaneously. And if all I do is just add the probabilities together, I'm double counting the probability that they fail simultaneously. Or that they're in the failed state simultaneously. So I need to throw out the overlap, which is why you have that additional term there. So AND gates, you use probability multiplication. So basically, if you go gate by gate, you get a 1.9 for this gate, you get a 1.9 for that gate, and then you do the same kind of probability math up here to get 3.44 E minus 1 for the total. Now, this is actually wrong. Why is this wrong? And I don't worry, I set it up to be wrong on purpose. And the reason is this power supply that is feeding the first valve is the same power supply that's feeding the second valve. These are the same event. So in order to handle this, fault tree analysis uses something called minimal cut sets, where instead of going gate by gate, the software will develop cut sets. What is a cut set? A cut set is a list of all the basic events that will cause the top event to be true. So if valve 1 is in the stuck position, you see an OR gate, you see an OR gate. So I know that event 1 being true by itself will make the top gate true. So what the software needs to do is get a complete list of all of the cut sets that will make the top event true. So in this very, very simple fault tree, we know that event 1 will make the top event true. Event 2 by itself will make the top event true. Event 3 will make the top event true. And this, what used to be event 4 that I'm now calling event 2, will also make the top event true. Now, where is the magic? The magic is the fault tree knows that this power supply failure and this power supply failure are the same event. How does it know that? Because you told it that it's the same event. Now, after creating the complete cut set, which is event 1, 2, 3, and 2, what the software does is it looks for duplicates and it will throw away duplicates. So using minimal cut set analysis, we calculate 2.71 E minus 1, whereas if you look at the gate by gate solution, it gave you 3.44 E minus 1. Why did I go into all this trouble to explain minimal cut set analysis? After all, the software does all this for you. Why do I need to know it? And the answer is, this is the reason why fault trees can handle the same equipment showing up in multiple protection layers, but a layer protection analysis can't.
Quick question, Ed. In this example, are both valves part of the same control system, either SIF or BPICS?
BPCS, Basic Process Control System. That is out of the scope of what I'm showing in the fault tree. I was trying to show something simple. So let's say for our purposes here that it's not. Because if they were, then we need to handle the commonality of the basic process control system too. Honestly, I didn't even think about that because I'm trying to focus on the small subsystem. But when we get into the bigger example, you'll see that you need to consider sharing of the logic solver also. And that'll come up when I start talking about the big butane overfill example. Good question, good point though. Okay, so now a few slides ago, I showed you a Lopa as a fault tree analysis where everything was independent. Now, let's look at that same Lopa, but instead of the protection layers being independent of each other, let's say that they have shared components. So how this is going to need to be drawn out. So let's say, for instance, that protection layer 2 and protection layer 3 share a BPCS logic solver. BPCS logic solver shared. What we need to do is then break protection layer 2 and protection layer 3 into multiple components. One is going to be the independent stuff. Let's say the sensor and the final element, and then the shared stuff, which is the logic solver. And also note, it's the same event. Event 5 is the logic solver, the shared component that is part of protection layer 2, and it's also protection layer 3. When I create my minimal cut sets, as you could see on the left side of the screen here, you'll see that this top event will be true if protection layer 1 fails. I'm sorry, if the initiating event occurs, obviously, and either protection layer 1 fails, this guy here, or the shared component fails. So this is one way to get to the top event. The other way to get to the top of the event is if the initiating event occurs and the protection layer 1 fails and the independent parts of 3 fail at the same time the independent parts of 2 fail. So this is kind of going into a little bit of detail into the math, looking at minimal cut set analysis to explain why fault tree analysis handles shared components where Lopa can't. And it's because we're going to break our protection layer into the non-shared parts and the shared parts, and the shared parts get treated separately, as we see here. Elegant handling. Okay, so that's kind of the mathematical underpinning behind what we're doing. Now let's go ahead and look at a case study. So this is from a refinery somewhere in the Midwest. This is actually part of their FCC unit. Those of you who know refining, fluidized catalytic cracking. And we're going to take butane is a feedstock. They don't make enough butane, so they have to buy it. And we're going to put butane into our our HF alkylation unit. So our FCC unit is creating a lot of olefins. We're buying butane. We're sending our olefins and our butane into the alky unit, and we're making highly branched paraffins, which have deliciously high octane ratings. All right, yes, I said deliciously high octane ratings. Somebody put that up on the quote board. All right, now the butane that they're receiving is coming in from a pipeline. So they've got a pipeline operating company that is sending them batches of butane, and they're going to fill this sphere. Now, when they are filling, the operator, so we're going to send an operator out to the field to calculate how much butane we need. And they do that by looking at the level. Well, I'm measuring the level 2 times. Once with LT101, once with LT102. And we really don't know which transmitter the operator is using to perform this calculation. Sometimes they use 101, sometimes they use 102. That calculates how much butane I need to transfer. Then the operator needs to take the amount they calculated and enter it into the flow totalizer as the amount of material I want to transfer. Then they hit start. When they hit start, it's going to open up this valve here, and you start filling material into the butane storage sphere from the pipeline. Now, if something goes wrong, there are high-level alarms on both of these transmitters. And also, for both of those transmitters, if either of them shows a high level, I have a safety instrumented system that's going to close UZV104 and stop the overfill. Now, there is a relief valve, but like most relief valves on butane storage spheres, they are designed to blow off vapor, not liquid. So if you liquid overfill, your PSV 121 is going to be of no use to you. All right, so we are in risk analysis mode. We want to put a SIL target on this guy right here. What is my SIL for this particular function? The first thing we do, our go-to, is to do a Lopa. Now, this first pass Lopa is a big honking, screaming failure. Everything that you could possibly do wrong was done wrong. So they said, well, the cause of overfill is that control loop. So this guy here, FQC105, that control loop fails. And we all know that basic process control fails at 0.1 per year. Okay. Actually, the initiating events are a lot more complex than just control loop failures. There's a lot of human factors that go into this. We'll come back to that. Okay. Now, someone said, well, I've got an alarm on level 101. I got an alarm on level 102. I'm going to take a 0.1 credit for both of them. No, you have two alarms, but you have one operator. I'm not going to go in. That's a whole other 1 hour class on how much credit to take in a Lopa for human beings, but we can only take credit for one of these if we're going to take any credit at all, and that's questionable. Okay, so I'll come back to that. So let's throw this out right out of the gate. Now, I have a SIL2 safety instrumented function in theory with a PFD of 0.01. So if my TMEL, my target is 10 to the minus 4, if I multiply these numbers together, I also get 10 to the minus 4. Everything's fine. I achieve my tolerable risk goals, right? Wrong. So number one, I threw out this additional protection layer. So I'm 10 to the minus, no, I'm still 10 to the minus 4. I digress. It doesn't really matter. But this initiating event, both of these alarm IPLs and that high level shutdown all rely on the same measurements. So in traditional Lopa, you can only use an instrument in one spot. So let's redo the Lopa using a more correct Lopa. So in our more correct Lopa, the first thing you'll see here is that we have the control loop failure. Oh, sorry about that. But we also added additional initiating events that are related to human failures. So there's a certain probability that the operator is going to miscalculate how much material needs to go in. So let's say they're doing 8 fills a year, which for this customer is correct. And let's just assume, using numbers out of this book here, initiating events, the CCPS initiating events book, that there's a probability of failure of 0.01 per opportunity. That gives me a 0.08 frequency that they'll miscalculate how much needs to go in dangerously. Also, they might fat finger what they type in. So they might have meant to type in 5,000 gallons and typed in 50,000 gallons. And that's going to be roughly the same number of opportunities to make a mistake at the same probability per opportunity of making a mistake. So we have these other initiating events that we're concerned about. Now, in terms of protection layers, we're going to say, yes, I am going to take credit for operator intervention for alarm 101, but I'm not going to take credit for alarm 102 because that's the transmitter I assume that the operator is using to make my calculation. So basically the Lopa is splitting things up, saying one of these transmitters is part of the initiating event. The other transmitter is part of the protection layer. Okay. So I can't take credit for this alarm because, well, I've got a common operator, and also common equipment. Now, SIL2 safety function, well, we can't take credit for it because its transmitters are being used for the alarm and the initiating event. So PFD of 0.1 essentially means I'm not taking any credit. So we did a similar analysis for the two other initiating events, ran through our analysis, and our first Lopa said we have no gap. When we redid the Lopa using the more conservative traditional Lopa rules, we have a gap of 260. We need a solid SIL2 risk reduction factor 260 to get to tolerable risk. So what does that mean? Well, that means I just bought myself 2 new transmitters, or 3 new transmitters, because I'm worried about spurious trips and I want to do a 2 out of 3 vote. So the recommendation out of the Lopa team was install 3 new transmitters for a 2 out of 3 vote for the shutdown system to have its own dedicated transmitters. This results in 5 measurements of the same device. Now, the Lopa recommendation goes up to the plant manager, and plant manager is not a sophisticated number crunching engineer, kind of a practical guy that came up through operations. And he said, tell me something. I have 2 transmitters already there. The maintenance records on those transmitters tell me that they work just fine. I haven't been having any maintenance issues with them. Why are you telling me I need 3 new transmitters when I have 2 transmitters already that work just fine? And that's when we said, well, Lopa said so. Lopa said so is something that you will find out that plant managers and CEOs don't like to hear too much, especially when it results in things that seem a little bit impractical and wasteful. So what did we do? I said, well, your procedures say to do a Lopa, but your procedures also allow you to do something that we at Connexus call a focused QRA. So if our Lopa is generating excessive recommendations, we can do a more detailed quantitative risk analysis to sharpen the pencil and get a more realistic assessment of the actual risk. And we will go ahead and run a fault tree analysis on this to determine whether or not we can get by with less transmitters. And that's
Hey,
what we
Ed,
did.
Hey, Ed, excuse me. We got a few questions out there.
Sure.
If there were multiple control loops still part of the same BPCS controller, would the initiating event frequency still be capped off to 0.1?
Okay, that's an interesting point of contention. When there are multiple BPCS failures, multiple control loops that can cause an event, that's something that requires a little bit of judgment and a little bit of analysis, because this frequency of a BPCS failure of 0.1 is already comically high. It's comically conservative. Its frequency should actually be closer to 0.03 instead of 0.1. So every time you add a new BPCS initiating event to a scenario, you're taking your comical conservatism and anteing up. So I personally like to lump multiple BPCS protection layers failures into one initiating event. That being said, be very careful when you do this, because different BPCS failures may have different protection layers associated with them. And also, there is no agreed upon guidance. So you can't find that statement in this book, for instance, that it's okay to do that. So I caution you to use your judgment, your best judgment and justification of what you're doing if you're going to do that. And that actually also might be a good reason to bring that scenario into a fault tree to justify why those multiple independent protection layers, those multiple BPCS initiating events, when added together, actually wouldn't exceed an initiating event frequency of 0.1. Good question. That comes up a lot.
Okay, there's also a question about the 2 human errors. Are they not part of the same procedure? Is the 0.01 per step in a procedure or for the overall procedure itself?
The probability of failure is for a task, for an activity. So a very long procedure could have a very high probability of failure because it has a lot of steps. I mean, and just, qualitatively, something that requires you to do 100 steps is going to have a lot more probability of failure than something that only requires you to do 2 steps. So the human error probabilities, and that actually is probably another good topic for a webinar, is human reliability analysis. But the numbers in the data books are based on a task. So if you go into like Swain and Gutman, some of the more detailed books on human factors, it's going to say, well, what is the probability that an operator goes to a valve manifold and picks the wrong valve, and gives you probabilities if all the valves are the same size, if they're different sized, if they're colored differently, if they're tagged differently. It is on a per task basis, not on a procedure basis. That's how the data was collected.
Okay. Someone was asking to see the drawing again as well. And there's an additional question here. Operator/alarm. In some studies, they analyze it with a fault tree. It is no longer direct 0.1. What is the correct form?
Well, okay. So remember, again, assigning a 0.1 probability of failure to operator intervention, and most of the time when you're in a Lopa, the failure of the operator to respond to alarm is a very specific taxonomy. An operator is sitting at the control station, an alarm comes in. The operator needs to verify that the alarm is valid. They need to determine what caused the alarm to occur. They need to determine what response action they need to take in response to that, and then they need to go perform the action. If the operator has sufficient time and the other criteria are met, that gets a 0.1 probability of failure. That's the traditional operator response in a Lopa that gets a 0.1. Now, that's Lopa. What we're talking about here is fault tree analysis. And when we go into fault tree analysis, we now are not constrained or handcuffed by the Lopa rules. But at the same time, we need to go into a lot more detail to make the assessment. So if you're in a Lopa, 0.1 is a conservative number to use in a given scenario under all of those constraints that I just listed out for the taxonomy that was just listed out. When you go into fault tree analysis, now you have more flexibility to look at what the specific scenario is. So I guess my comment there on the big picture level is that the simplified Lopa has a lot of conservative rules attached to it because you're trying to do a lot of risk analysis quickly with minimal input. But when you shift over into fault tree world, now you've got more flexibility, but that also requires you to do a lot more analysis of what the actual situation is and a lot more research in terms of justifying and getting traceability for the numbers that you're going to put into your fault tree. All right, well, let me go on, and I'm going to start because we've been going at this for a while. So let me kind of hit the fault tree real quick, and then I'll do more Q&A at the end. So just let me just go through the fault tree here. Okay, so I built a big fault tree, and what the fault tree for this scenario does is it's going to consider all the causes, and it's going to look at initiators. The initiator is kind of weird in this case in that it's not a failure of a piece of equipment. It is the fact that I attempted to perform a transfer. So my initiating event is 8 times a year, I'm going to push the button to start a transfer. That's the initiator, which makes it a little bit kind of different from what you typically think about in a Lopa. The causes of failure then, as a result, need to be conditional probabilities on a per transfer basis. So now I'm going to show you little snippets of the fault tree, and then I'm going to come back and go into our fault tree software and show you the whole thing, what it looks like. So part of the fault tree, gate 4, is I am going to attempt to transfer an amount of material that's in excess of what can be transferred into that tank. Why would that happen? Well, that means the reasons that I would send an excess amount is if I just failed to compare my level transmitters against each other to realize that one of them isn't working, and then I looked at one of those and I calculated an amount of material that is in excess of what the available space is. So either I didn't check to make sure that there was a failure, or part of that needs to be that one of the devices failed. So there's part of it here is the device failed and I forgot to check it. And I have 2 devices. So I'm assuming that I'm making the conservative assumption that I'm going to read the wrong transmitter, the failed transmitter. That's why you have the OR gate here. Next thing is the failure of operator intervention. And here you'll see I've got something highlighted in blue because I want you to see that this is showing up in multiple places in the fault tree. And when we do our minimal cut set analysis, it's going to get tossed out. So part of the tree talks about failure of the operator to stop the transfer. That's one of the IPLs in the Lopa. And you'll see that in the Lopa, I just have a 0.1. But here, I've got 1, 2, 3, 4, 5, 6, 7 events that break down that one IPL in the layer protection analysis. So you see that the fault tree analysis is a lot more rigorous. It's a lot more work because you're taking that IPL and breaking it apart into the individual components that define it. So one of those components is the operator does not respond to the alarm. Another component is that the logic solver fails. So the logic solver didn't display the alarm to the operator. Another component is that the level transmitters fail dangerously. And because it's kind of a 1 out of 2, but I have 2 transmitters, that's going to be an AND gate. Okay, so now you see that when we start looking at our protection layers in a fault tree, it's a massive breakdown into all the individual separate ways that things can fail. But now, here, that level transmitter failure is gate 12 and gate 13. Gate 12 is LT101 fails. Gate 13 is LT102 fails. All right, let me go ahead and show this fault tree. This is what the top event is. And at the top event, we said I attempted to transfer an excess amount of material into the tank and all of my safeguards failed. The TMEL was 1E minus 4. I calculated 7.58 E minus 5 with only 2 transmitters. So ultimately, this fault tree showed me that I don't need the 5 transmitters. The 2 transmitters were just fine. Now, what we ended up designing was a 2 out of 3 vote. So we did add another transmitter, but we didn't need the 5. We demonstrated that using the fault tree analysis. Okay, I'm going to go into a little bit more detail when I show you the fault tree. So let me jump out of my presentation here, and I'm going to go into our software. So Arbor is part of the Connexus Integrated Safety Suite, where it's our enterprise tool for doing basically all things technical safety. So I'm going to log in with single sign-on. I'm going to go into EMM samples, overfill FTA case, and here is our fault tree. Okay, so this is the whole entire fault tree. And let me zoom in to make things a little bit easier to see. You'll see that the overfill event as a whole is here, and you'll see that we've achieved our tolerable risk. I am going to get an overfill if I attempt to perform a transfer and, this is an AND gate, all of the protection layers fail. Now, I'm going to attempt to perform a transfer 8 times a year. See, W equals 8, and it's an initiating event. And I fail to perform the transfer correctly. So when you see this little appendage to a gate, that means that there's stuff underneath it. So let me show you the stuff that's underneath it. That is gate 3. Fault tree page is gate 3. So this is gate 3. So I'm going to do that when I miscalculate. I'm going to do that if I enter the wrong amount. And I'm also going to do that if the level transmitter has failed. So with a level transmitter failing, again, that's gates 12 and 13, events 15, 7, 5, and 16. So if I go back to the top event, why would my safeguards fail? Well, my safeguards will fail if the relief valve fails. And we said we're not taking credit for the relief valve because it's not sized. So I put it in the fault tree, but I made it always true, meaning it will always fail because it's not sized for the scenario. It will also fail if the operator fails to stop the transfer. So this is my operator intervention, and this is my safety instrumented function. My safety instrumented function will fail if the transmitters fail, if the logic solver fails, if the valve fails. Actually, gates 15 and 16 here are both part of the same final element subsystem. So if you look at it, you'll see that your fault tree that you would do for a SIL verification is sitting here inside your fault tree. The fault tree allows you to combine everything together. But notice, inside the fault tree for the safety instrumented function, gate 13 and gate 14 tell me that the level transmitter has failed. If I go into the operator intervention, which is going to be gate 6, gate 12, and gate 13, tell me that the level transmitter failed. If I go into the initiating event for the butane transfer, the butane transmitter will fail if gate 12 or gate 13 are true. So you'll see that that level transmitter is in the initiating event fault tree. It's in the operator intervention fault tree, and it's also in the SIS fault tree. The fault tree analysis software knows that it is the same piece of equipment in all those places, and due to minimal cut set analysis, it can elegantly solve for the solution, knowing that the same device is being used in the initiating event, in the operator intervention, and in the SIS. This is a great archetype for the use of fault tree analysis because it demonstrated I didn't need 5 transmitters. I could get away with 2, the 2 that were already there. But the fault tree understood those 2 transmitters are part of the initiating event. They're part of the BPCS or the operator intervention protection layer, and they're also part of the SIS, and that's okay. All right, so with that, let me jump back into the presentation and hit some summary points. Lopa is ubiquitous. It's a great tool. Lots of people use it all the time. But simplifications that are cooked into Lopa sometimes prevent you from accurately calculating the risk. And these simplifications sometimes result in poor design recommendations that include a lot of redundant equipment that you might not need. And when you get 5, 6, 7, 8, or 9 of the same device, that might be a clue that you're overcooking your results using the Lopa. Those potential over designs have a potential high cost, both capital and operating expenditures. If you're doing a Lopa and it starts to give you crazy results, investigate the root cause of why those results are crazy. And sometimes it might be the inability to consider protection layers that have common equipment. And sometimes it's that you have a very complex scenario that you have oversimplified. When you run into these situations, it is a good idea to supplement your Lopa with a fault tree analysis, because the fault tree analysis is going to be able to address those shortcomings due to the more sophisticated analysis techniques that are available in a fault tree analysis that are not available in your typical layer protection analysis. All right, so hopefully everybody was able to keep up with that. I know that once we got into the big fault tree, there's a whole lot of information there to try to keep track of. But before I open the floor to questions, I will let you know, send us an email if you're interested in getting the paper. We'll go ahead and email that out to you. And with that, let me go ahead and open the floor to the balance of the questions that might have been generated.
Joe, I have a quick question. This is Manuel Erce. So I heard you say something along the lines that if you have trouble kind of proving independence from some of your IPLs, you recommend the use of fault tree. My question is are there any restrictions for still meeting SIF criteria or SIL criteria for those?
Okay, well, ultimately, let me get out my dog-eared, tired copy of IEC 61511. Ultimately, I'm going to a specific clause in clause. All right, so there are a couple clauses in the standard that you're responsible to achieve regardless of whether you do a fault tree or not. So clause 8.3.2 says the average frequency of dangerous failures of a BPCS as an initiating source shall not be assumed to be less than 10 to the minus 5 per hour. So,
no, but I was not talking about the BPCS part. I guess in your example, when you're analyzing the alarm and the SIS, or that it was a SIL 2, they are not independent. So they was a good example for showing that they're shared component and they were not independent. But by using the fault tree, you can achieve it.
Right, exactly. And we were able to do that. So in your typical assessment process, you do your risk analysis, assuming the SIS is physically and functionally independent of all the initiating events and all the protection layers. And that allows you to do your LOPA and your SIL verification independent of each other because they are physically and functionally independent. When your LOPA and your SIS share components, you can't analyze the risk separately anymore. That's why what you saw is that same fault tree that you would do for your SIL verification resides inside your overall risk analysis of the plant. And it's basically, we are using a more sophisticated approach because the assumption of independence isn't there anymore. So there's no documented restriction on doing what we did. And furthermore, when you showed that your target maximum event likelihood was achieved, you have effectively proven that whatever performance you're getting out of the safety instrumented function that's already there in your fault tree, by definition, has to be adequate to achieve tolerable risk. So the standards are all making simplified assumptions about what you're doing. And, you know, some of those simplified assumptions include independence and preventive protection layers. So when your real situation doesn't match those simplifications, you have to use your engineering judgment to most accurately model reality. And in terms of restrictions, either from the 61511 standard or OSHA PSM rule, I don't see any restrictions on the extended fault tree analysis. It's something that not only do I not see any restrictions, if you look into clause 9 of the standard, it actually recommends that you do this type of analysis. I don't want to delve too deeply in, but yeah, clause 9.2.7 says, you know, if you're getting SIL 4 or getting unacceptable risk analysis results, it says a further risk assessment shall be carried out using quantitative methodology to confirm that the safety integrity requirements are achieved. So even in the 1511 standard, it recommends that if your Lopa risk assessment isn't achieving reasonable results, you should be doing something more sophisticated. So I don't really see any conflict with any standards that are out there and the more sophisticated fault tree approach that we're talking about here.
Thank you.
Sure.
Okay, another question here in the chat from Tim. It says, can Arbor account for beta, or does common cause need to be explicitly modeled, as in beta factor as a percentage?
Okay, that's an interesting question, because there are some software tools that are competitive to Arbor that allow you to define beta factors and assign them to events. We don't do that. We want you to explicitly define what the common cause is and show it in the fault tree. We deliberately chose that approach because in some of the other fault tree tools, when you just define a beta factor and assign it to pieces of equipment, sometimes it will calculate things in ways that you would not know, understand, or expect it to. So we want you to explicitly define what the beta factor is by calling it out as its own separate event in the fault tree. So I understand that's a little bit more work, but it's going to avoid errors and force you to understand what you're doing when you're defining common cause. So nope, it's not automatic. You have to define it yourself.
Okay, thanks, Ed. There's also a request to see the fault tree analysis one more time. They'd like to see what the end result and what it dictates.
Okay, the end result and what it dictates. So let me jump out of here and I will go back into the software because that allows me to jump around a little more. So let me shrink things down a little bit so that you could see more. So I'm going to basically paginate so that you can see everything on one page, and maybe let me screw the view up a little bit. So this is the kind of the top line, if you want to think of it that way. On the left is kind of the initiating event. On the right is the failure of the protection layers, if you will. And granted, down at the bottom, there's a bunch of shared stuff back and forth. But ultimately we said we have a target maximum event likelihood of 1 in 10,000 chance per year. We calculated a frequency of 7.58, 10 to the minus 5. So the estimated frequency is less than the target frequency. So the equipment that we've defined, including only 2 transmitters in a 1 out of 2 vote, is able to achieve tolerable risk. And that is based on the fact that the safeguards will fail at a probability of 2 times 10 to the minus 4. And our initiating event frequency is going to be at about 3 times 10 to the minus 1. So about once every 3 or 4 years, we're going to try to overfill it, but we've got 1 in 5,000 chance of failing our safeguards when we do that. So this is kind of the big picture. Hopefully that answers the question of the person in the chat.
Okay, yes, that does answer it. There's a question here. Does this also show shared IE and alarm DCS?
So if you think about this in Lopa, this here is telling me my initiating event. Then I have 3 protection layers. One is the relief valve that I didn't take credit for. One is operator intervention. One is the safety instrumented function. So if I drill down into the operator intervention safety function, you'll see it's not just a 0.1, it's a bunch of events. And you'll see this little, you see a chain and a 2. That basically is the software's ability to say, hey, this event is showing up in 2 other places beyond what you're looking at here. And if you look here, it's saying, hey, this gate is showing up in 3 other places than what you have here. Okay, but going back to the operator intervention, you'll see that we have the operator doesn't respond or the alarm fails. And the alarm fails if either the transmitters fail or the logic solver fails. Now, very interesting question, because I didn't remember this until the question was asked. The alarms that the operator is responding to is off of a pan alarm, and the alarms are generated by the SIS logic solver. So the transmitters are wired into the SIS logic solver, and the SIS logic solver is also generating the alarms, which, if you want to criticize me, I should have put another event in here related to failure of the pan alarm annunciation device. So excellent question, but the DCS was not the mechanism that enunciated the alarms in this case. It was a pan alarm device that was driven by the SIS logic solver. Good question. Man, I love the good questions. Make me think and keep me honest, because I now noticed that I didn't put the pan alarm in here. Good catch. Anything else?
I think that's it that I see. Someone asked about a trial of the software. I put in the chat that you can request a 30-day trial.
All right, so yeah, www.connexus.com. If you go to software, fault tree analysis software, click down here on trial request and pricing information. And when you click right here, it's going to ask you to fill out this form. When you fill out the form, it's going to send about 7 of us an email, and someone's going to hit the approve button. You'll be good to go.
Sorry, I have a question.
Yeah.
Question on looking at, have you ever come across a situation where a company wanted to do, we'll call it a base fault tree analysis that could be, let's say, it would apply to 80%, 75%, whatever situations that are found. Have you ever seen a company build we'll call it a database of 10 or so of these fault trees that could be utilized within any plant's,
Absolutely.
hazard scenario. And have you been involved doing that? And would you support
Absolutely.
the company in doing that? So
Yeah, absolutely. It's a topic for another day, but I am a huge fan of templating. I believe that the greatest tragedy in technical safety is the great preponderance of the time teams doing a risk analysis start out with a blank sheet of paper when their organization has done dozens or hundreds of analyses of the same freaking scenario. And you're starting from a blank sheet of paper with a group of people that are 2 years out of college and have no experience with the hazard scenario that you're talking about. I'm a huge proponent of templating as a starting point. And templating is a starting point for HAZOPs. We have the ability to template HAZOPs. We have the ability to template LOPAs, and fault trees is another case. So there is one customer of ours that is a big proponent of doing templates. So we've been involved in helping them develop fault trees for what good looks like for a variety of applications, including they're an oil refining organization, so they've got a template for runaway reactions in hydrocrackers. They have a template for runaway reactions in heavy oil hydrotreaters. They have a template for every hazard that's protected by an SIS and a fired heater. So low fuel gas pressure, high fuel gas pressure. They have a template for anti-backflow shutdowns in hydro processing equipment, so hydrocrackers and hydrotreaters. And we at Connexus have helped them to develop all of those templates. So it's something that we have done, we have experience in. I cannot possibly promote it enough because it's such a good idea. And you don't need to go into the super detail of a fault tree unless it's a complex problem. But please put those templates together for your LOPAs and your HAZOPs of your very common scenarios, like fired heaters, heat exchangers, reactors that you run into a lot. Templating, underutilized, extremely valuable tool.
Okay, there's a question about, is there event tree analysis software, or is it all just done in the fault tree analysis?
Right now, we don't have event tree analysis software that is publicly available. I know that sounds weird. We have a tool called Quantum that basically is going to be Connexus's replacement for FAST when we get it done. It has an event tree module, but that's only available internally to the company because it's not ready for prime time yet. But we do have our quantitative bow tie analysis tool that will allow you to do something like an event tree where a single loss of containment scenario has many different consequences. So it's possible in our quantitative bow tie software. Our event tree software is not ready for prime time yet. Give me a year.
Yes. In your FTA, you included the SIS loops.
Yes.
But isn't it our objective to ensure that the system works within the tolerable risk limit without the SIS loop? And then if it does not find a SIL target for the SIS loop, so why include the SIS loop in the FTA at all?
Well, because in this case, our SIS is not independent. And an option would, I mean, that you're absolutely correct. And there is a conservative design practice that says, no, I'm not going to share those two transmitters among all these protection layers. I'm going to have separate dedicated transmitters for my safety instrumented system. But in this case, it would have required the installation of 3 new transmitters. And the plant manager didn't want 3 new transmitters and wanted a quantitative justification of why he needed to buy those 3 new transmitters. And our quantitative analysis showed he didn't need to buy those 3 new transmitters. So there's a judgment call that says qualitatively, I want my SIS to be fully, physically, functionally independent. And I completely respect that. Completely respect that. But the math shows that they don't need to be. And that's what we showed here. And if you get into that situation where you need to justify the fact that these transmitters, like the last person just talked about, these 3 transmitters are going to the SIS and they're going to the BPCS. Is that okay? We could do a quantitative proof that it is okay.
Okay, thank you, thank you. But if you are governed by 61511 or 508, when they say physical separation is a must, right? It's just given. Then in that case, like regardless if you do a fault tree or not, you might as well have to do a redundant transmitter for your SIS,
but
right?
Physical separation is not a must. Let's pull up the standard here, and I'm going to go to clause 11.2.10. There's another webinar on shared components where I go into the standard 61511 standard in detail, more from an SRS perspective than a Lopa perspective. But the standard says a device used by the BPCS shall not be used by the SIS where a failure of that device may result in both a demand on the SIF and a dangerous failure of the SIF, period. Oh, wait, no, there's no period there. There's a comma, and then another clause that says, unless an analysis has been carried out to confirm the overall risk is acceptable. And what does that analysis look like? The fault tree that you just saw.
What clause is that, Ed?
11.2.10.
Thank you so much.
Sure, absolutely. I appreciate your attention. I appreciate the attendance. Keep an eye out for more of these. I encourage you to go back and look over the recorded ones because we don't do repeats here. They're all live presentations. Chris, go ahead and close us out.
I'm going to go ahead and end the webinar. And if you need anything else from us, just let us know. Thank you, everyone.
Thanks, everyone.